So welcome. The lecture today is on fastslam. Fastslam is the application of particle filter for the slam problem. So what you've seen on Monday, the last part of the lecture on particle filter, and how we can now apply this technique to solve the slam problem. As we have seen on Monday, particle filters are a non-parametric way of in solving the recursive bias filter equations. We have, instead of representing the belief as a parametric distribution, we just represent it as a set of samples, and we will associate a weight to each sample in a way that each integral, each expectations of this distribution approximates the relative expectations and integrals on the original distribution. In this way, they can model arbitrary complex distribution, not just limited to any parametric family. And if you have low-dimensional spaces, works quite well. But what we'll see today is that if we have a higher dimensional space, then there are some problems that we need to address. As any Bayes filter, they follow the usual prediction update cycle, and according to the implementation of the particle filter, some of them have an additional step, which is a resampling stage. So as we can see here, we have these three steps. This sampling from proposal is kind of equivalent to a prediction step on the Kalman filter, on the Bayes filter. The importance weighting will be the equivalent of the update step, and then we have a resampling, which just is something needed for mostly for computational problems, so that we can focus the density in the right part of the samples in the right part of the space where it's more dense. And in principle, one can also go without that, but in practice, you will need more samples than using a resampling step. So, as you have seen, the steps now in more details. The first one is the sample. So we define a distribution. We call it now normally pi. And it's a distribution over the state space, x. And we get a sample out of it, which indicates with x with j up there. Once we have this sample, we use the importance sampling principle to compute the weights. And the way we do the weight is we take the target distribution evaluated at x, j, the sample that we just computed, and we divide by the value of the proposal distribution also evaluated at the sample j. Once we have this weight, we can resample these samples that we have according to the weight. And we do it for all the samples that we actually need to have, and then we somehow reset the weight of each particle to 1 over the number of particles. Okay, we have seen also that in short we can define a sample set x as a pair of sample and weight, and this will define completely our distribution. And you can also think of each of these samples as an hypothesis on your state, and you can, but a bit more loosely, think of this weight as how important or how good this hypothesis is, but that's not always true. It just depends on where you sample x. So if you sample x from a uniform distribution, then you can imagine that W is the how likely or how good this hypothesis is. But if you sample, for instance, x for any other distribution, then this will just identify the mismatch between the distribution you use for sampling at that specific point and the real distribution that you want to have. Okay, so the way of seeing these samples as likely hypothesis is more like looking at the neighborhood and seeing how many of them are around it. Okay, when we want to apply the particle filter on SLAM, the first thing we need to consider is what is in here. So what is the state space? And today we'll talk about feature-based SLAM. So we will have as a state space a part which is the robot pose, and we will have it from the beginning of the life of the robot up to current time t. So on the contrary, what we did with the Kalman filter, we will not just estimate the last pose of the robot, but we will just estimate the full trajectory. And then we have the usual set of landmarks. In here we will call them M1, M2, M3. And we have, of course, the X and the Y of this landmark. So we are considering now H2D cases, but can easily extend it in 3D. We'll just put the Z here. So these landmarks are just point estimate, so just points in the environment. Okay. So as I said before, one big problem of particle filter is when the dimensionality increase. In this case, we need to take into consideration how coverage of a high dimensional space might work. And you can see if you have a very low dimensional space, like a 2D, you can cover it with a set of n particles, let's say, so n samples are okay. But if you, for instance, add the third dimension, then you can imagine this layer of n samples should be replicated on, like, ideally in the third dimension and so on. So the more dimensions you have, if you want to cover the space in a good way, you have an increase of samples that might be too much demanding for computational purposes. So we'll see later on how we can actually handle distributions and how can we handle the posterior that we want to estimate for SLAM, exploiting the structure of the problem and find a better way of doing sampling there. So if we now see our variables here, we have the pose and we have the landmarks. We can exploit some properties of the inherent graphical models that we have behind. So one thing we know is that if we know the poses of the robot, okay, then we know that all these landmarks are actually independent, and we know how to compute in closed form an estimate of them. Okay, that's because in the most naive case, we will just take the pose of the robot, all the measurements, and we'll just put anchoring all the measurements down with respect to the pose of the robots. We can just render all the data that we collect, and this will already give you an estimate of this landmark. Okay, so the core idea here is that if we can just estimate the pose or the trajectory of the robot with samples, then we compute the landmarks analytically after that, we already reduce a lot of dimensionality because all of these do not need to be sampled any longer. Okay, and that's the idea of fastslam, and that's the idea of reducing this dimensionality into something which is more manageable and more tractable. This whole idealistic or intuitive way of doing that actually stems from a strong statistical background. There is a theorem from Rao-Blackwell that basically says that if you are able to if you want to estimate the distribution over a certain state space, and you know that once you know part of the state space, you have an analytic form for estimating the sufficient statistics, says in the theorem, but in principle you can imagine if you have a closed form way of estimating the parameters of this distribution, okay, and then it's always better to estimate this, and then using the closed form analytic solution that you have for that, than just estimating directly this one. So the theorem says that the variance of the estimator, which is basically a way of saying how good an estimator is, if you do like this, or if you do it directly like this has always less or equal variance than the other one. So it's never worse to do it in this way, but it's often better. That's let's say the gist, the take-home message of this theorem. For what concerns us, this basically says if we can sample from here and evaluate the parameters of this distribution, or you can estimate part of the state B or the statistics of B given A in an analytic way, then doing this estimation is no worse than doing that one, and it's normally better. So this, instead of sampling directly from here, we can then sample here, doing our analytical evaluation, and we get our final distribution out. Okay? Is it clear? And that's now getting back to the SLAM problem and see which part of the state we can play and which part of the state we can estimate. So if we go back on our usual distribution, so we have the poses, the landmarks, the observations, and the controls. We can decouple this by just using the chain rule, so we just bring the map on the back. We can we just put the trajectory on the back. We can see that we have a distribution over the trajectory here, given the observation and the control. And then we have a distribution over the map, over the landmark, given the poses and the observations. And here, by exploiting Markovianity, we can remove the control there, because the landmarks do not depend on how the robot reached different places, but just depend on where the robot is at a certain time. Okay? So, can we compute this efficiently? The answer is yes, and that's because we can have we can collect all the observations that falls from one landmark, and then we can just estimate them by using, for instance, the mean can be an estimate, the variance, and basically what we will do later on is that we will use a set of independent Kalman filters for estimating each landmark on its own. If you get back on the graphical models, this is our trajectory, okay? These are our controls, these are observations, these are our landmarks. If we now know all of it, we can directly see that all these landmarks are actually independent. No? You can see it because there is no path from here that actually reaches the other landmark there. No? Because when you go up here, this path is blocked because we know the value of x. If we didn't have the old trajectory and just the last pose, then this was not true any longer, because we could still go up and then down because we didn't know these guys there. Okay, so the path was not blocked because we didn't condition on the state at that time. Okay. So, given that they are conditionally independent, we can also now write this distribution as a product of independent distribution for each landmark. We estimate this by just a set of two-dimensional extended Kalman filters. Okay, so this is the idea. And then we can estimate the trajectory with a particle filter which is quite similar to what we've seen on Monday, which is Monte Carlo localization. Because at the end, we just do not have an explicit map here. So the way we compute the weights will be slightly different. But in principle, we still sample from a motion model, and we still evaluate then our weight considering the ratio between the proposal and the target distribution in that case. So the sample-based representation that we have will be the same, will be very similar to Monte Carlo localization. It's only that instead of having one sample for a pose, we have each sample representing a full trajectory of the robot. Okay, so we will have, as it's written here, a path hypothesis. So we have an hypothesis of x at time 0, x at time 1, time 2, and so on up to the time where we are right now. And the interesting key idea is that we do not really need to revise past sample poses, but we will see that we can actually sample a full trajectory incrementally over time as a new robot control comes into play. So if we have now this in mind, we can also see it more on a structural and construction point of view. We have a lot of different particles, so the samples. Each of them contain an hypothesis over a trajectory. So this will be, we just omit the index, but it will be x, y, and theta over time. And then it contains a set of landmarks, landmark 1, 2, and m, which is the landmarks that, according to this sample, we have observed so far, and also contains the estimate for this landmark. So if you want to have an estimate of the map, we can just take the expectations over all of this, assuming that they have the same dimensionality and we are able to associate the different landmarks from different particles. And we can just take the integral again over the particles weighted by the weight of the sufficient statistics of this. No? So this is something that we can do, or we can just use as an estimate the most likely hypothesis. So we do a maximum a posteriori on the pose, and then we take the landmark associated with that. So we can again play with which kind of estimate we want to take, since we have a full joint distributions of them. It's just one part is discrete, made out of samples, and another part is continuous, which is made of this Gaussian estimate for the individual landmarks. Okay? Ideally or intuitively, this works something like that. So imagine that these three are three different samples of the poses, and each of them has its own AKF estimate of these two landmarks associated with them. No? So they will be in different parts of the state space, and also the statistics of these landmarks will be slightly different. The first thing that we do is an update. So we take our motion model, we sample out of our motion model, and then we compute the next pose in the trajectory for each of these individual samples. Okay? And our trajectory sample will just be the concatenation of the trajectory sample we had up to here, and plus the new one that we just sampled right now. Okay? So this gives another set of hypotheses. We then obtain some measurements, and for each particle then we can reproject the measurements into the state space in the global frame. For this one, they will end up in here. For this other particle, they will end up in here, and this other one over there. Okay? Once we have that, we can compute the weight, and we'll see that the weight actually accounts for, in some sense, the mismatch of the observations projected down in the global frame and the estimate of the landmarks that we have. So in some way, similar to what we did for Monte Carlo localization, where we had the mismatch between the measurements and the map that we had. But in this case, our map is actually a stochastic map, because we have some uncertainty for each of these landmarks, and then we need to take this one into account as well. Once we compute the weight, we can also do an update of the estimate of the individual landmarks. This is just done by the AKF update rule that we've seen during the first part of this lecture. And this make a decrease in uncertainty for each of these landmarks, and also a change on the state estimate on the mean of this distribution. So how do we do mathematically all these steps? So the sample, the sampling is done in this way. We use as a proposal distribution something which is the motion model from the previous step, and this will just add the next sample in our trajectory, and we will use then we'll concatenate this one with the sample that we had before. So if you remember from Monday, we said that when we do resampling in a particle filter, it's like sampling from the target distribution. And basically, to concatenate this one, we first do a resample from the previous sample set of the trajectory. This will be sampling from the trajectory distribution from 0 to t minus 1. Then we sample from here, so that we have the sample for t, and we concatenate them together. Okay? And to compute the particle weight, then we will use this expression. This basically is telling us that we want to have a Gaussian, because each of these landmarks is a Gaussian. If you put them all together, we have a multivariate Gaussian of higher dimension. We need to compute this Q, and we'll see how we will compute it later on. And then we also need to compute the prediction from each individual particles, okay? And this prediction will be then computed using the measurement function that we have for the usual linear or nonlinear extended Kalman filter approach. And we just consider that this part of the state is deterministic, which is the particle, and the only thing which is stochastic will be the part that considers the map, so each individual landmarks. And this is our prediction. We take the difference and we compute it in this way. We'll derive this later on to give you a better idea on where it comes from. So if you want to see it in pseudocode, what we do is we have this as our particle set. So each particle has its own previous pose in this case, but you can imagine that this has attached all the past poses. We don't do it explicitly because in theory you should have a sample of the whole trajectory, but computationally the previous samples will never be used in the next step. So it also doesn't matter to include them when you implement the particle filter directly, because they will just be they will just use memory, but it's values that you will not use in the future. But you need to consider them because you have you will see that there is a theoretical reason why we need to sample from the full trajectory. So, but that's why you will always often see only the last pose when you see a particle filter on the trajectory for SLAM. But this is just because it's more for a memory consumption point of view. But from a theoretical point of view, you should keep the whole trajectory there. We sample now the next pose from the motion model. And then again, we check if we haven't seen this feature. So we do our usual known data association. So we take the index for each observation of which landmark we are actually looking at. And if you have never seen it, then we do the usual initialization. That's the same as we did for the Kalman filter for the AKF SLAM. And instead, we compute the AKF update as we did for the extended Kalman filter, just for the landmark in this case, but it will be the same equation, compute the Kalman gain, the innovation, and update. And then the new step here is to compute the weight according to this Gaussian distribution here. That's the likelihood of the observation. And this is equivalent to this expression. One thing to take into account is that this h is the Jacobian of your measurement function, but with respect to the landmark and not with respect to the robot pose. And that's because the robot pose is in a way deterministic. It's one sample, it's just one potential hypothesis. So as a distribution will be seen as a Dirac delta. Therefore, there is no uncertainty in that. So it doesn't come into play. This covariance matrix is also the covariance matrix of the landmarks, and there is no uncertainty in the robot pose modeled by that. Okay? And this Q again is the usual sensor noise that we have from our laser or sonar or camera if you triangulate whichever sensor you have. Once the update is done, we change the particle set for the landmarks that have been observed. We keep the landmarks that have not been observed as they were before, so they just do not change. The only thing that we do is we just put them back into the particle which is there. So we just need to be sure to make everything consistent. And then we do a resampling step using stochastic, so the sampling algorithm that you've seen on Monday, so universal stochastic sampling, resampling, and so on. And at the end, we just return the particle set outside. So that's the pseudocode of the fastslam 1 algorithm. If you want to do the Kalman filter update, these are again the usual equation for the Kalman filter update of each landmark. We have our measurement function. Our h now is the Jacobian of this function, and is only with respect to mu in this case, which will be the landmark part, because this one is something that we actually know. And we compute the usual q, k, and we do the usual Kalman filter update. This is how the filter works in practice. What we have is here you can see the trajectory and the ground truth. So you can see in the dash thing is the odometry, if you just go for the odometry. The red one is the ground truth. The blue one is the best particle, so the best trajectory from the particle set. In this case, we will use the one with the highest weight, but just to give an idea on what's happening in there. And you can see that this estimate is quite close to the ground truth, while the odometry, as usual, is going kind of far away. And you can see that close by to the initial pose, we have very good estimate of the landmarks. If you go far away, the uncertainty still comes into play, and so on. So the usual problem with having a higher uncertainty away from the initial position is also happening in fastslam. Now, we said that the weight comes from this ratio here. So we should take the target distribution that we want to estimate, divide by the proposal distribution, and this gives us this nice Gaussian that you've seen before. But probably you now wonder where and how we can get from this to this nice expression there. The reason is very simple. So if you just take the ratio, it will happen that we have this as our target distribution. We have this as our proposal distribution, which is decomposed in this way. We have our sample part down here. This is the part of the trajectory that we are somehow neglecting in the algorithm, but it's still part of our sampling process. And here we have the last part of the trajectory, which we just sample using the motion model. So this one comes from the resampling step of the previous step of the algorithm, previous time step of the algorithm. This one comes from the motion model that we have using the control of the robot. If you now take the ratio between these two, and we also take care that x is always considering by a particle, so it's not a variable any longer. This will be x equal to xk, so this then becomes somehow a likelihood function, and the same for the others. If we now expand this and we do Bayes rule and factorization, we end up with the usual flipping of the observation on that side, comes here, the usual Markov assumption of not considering the odometry any longer in this part here, and then we have our nice decomposition of the distribution of the time before considering the motion model, and down here we have the recursive part on the Bayes filter. And that's the usual decomposition we have seen always when we talk about the Bayes filter. No? We do Bayes, Markov, and we have this nice decomposition. When we do the filtering in just the current pose and not the previous one, you normally have an integral here because you marginalize over the previous pose. Since now we are considering the full trajectory, we do not integrate any longer because the previous part of the trajectory is still in the state space that we are trying to estimate. If you now take our proposal, as we said, it's a part of it is the motion model, so it comes from the directly sampling from the motion model, and another part of it, the one that regards the previous part of the trajectory, just comes from the resampling step of from the previous time step. So these two things are actually the same. These two things are actually the same. So we can just simplify and cancel them out, and what ends up is just a likelihood of the observation given the pose of the robot, actually the full trajectory of the robot, and the previous observations. Okay? So that's what we have as our weight distribution. Now, the interesting thing is we cannot really compute this in closed form or analytic form because we don't really have a direct mapping between the current observations, the previous past observations, and the robot pose. The only thing that we know how to compute is a likelihood considering a map of the environment. Now that's what we know. So a way of getting this is just to marginalize over all possible landmarks. No? So basically you say, I have a map here. Now I can just consider one landmark at a time for simplicity. So I'll just have MJs, which is the jth landmark that my measurement is associated with. But in principle, this can be the whole map, and this can be observations of the whole map at the same time. No? The idea here is, since we do not know how to compute that, but we know how to compute these things, and we have this part here for each particle, which is done by this individual Kalman filter. We can actually compute this integral, okay? And I'm not going to do the integral completely, but it's the same trick that we did when we were devising the Kalman filter from the base filter, that you complete the square, and then you know that if you put the form of a Gaussian distribution, which just depends on m here, you know how to compute this integral, and then the normalization factor of this will then be the output of that. Now that's the usual trick of completing the squares. If we do that, we end up in having a normal here distributions. We know that this is a convolution between two normals, and we have this expression down there, where this is the Jacobian of the observation function with respect to the landmark, which is the one that we use to compute the z hat in there. We have, this is the uncertainty of the landmark, which is the same uncertainty that we have here in the estimate of our landmark. And Qt is the uncertainty of our measurement model, okay? So this comes out because part of this distribution plays with this distribution. When you multiply through exponential, they just comes together in the same exponent. And when you put them aside, they just end up in this form here. So if you look at the way we derive the Kalman filter, you can try to derive these things also on your own, knowing that this is a normal distribution with this expression, this is a normal distribution with this expression. Okay? And that's then exactly what we have here and we showed before. So this nice expression comes exactly from taking this ratio from the proposal distribution that we use, from the target distribution that we want to have samples from, and the proposal distribution that we use. Okay? If we change the proposal, and that's something that actually also has been done for fastslam, there's an advanced version, we'll see later on, you also need to change the way you compute the weights, because those two things are actually correlated and constrained together. So this is exactly what we have seen in the step before in the pseudocode. Now we have thought right now that there is an oracle that gives us a data association for each observation to whichever landmark in whichever particle they belong. Okay. Now the problem here arises on data association. So if you have a situation like this, when the robot is here, he has inside his estimate 3 different landmarks. Imagine this is now one particle, so one pose of the robot with certainty. And now he has these observations here and there. It's not really clear why we should associate these 2 observations to these 2 landmarks or to these 2 landmarks, because they somehow lie in between them. Okay, so it's a very hard data association problem. And if we use algorithm like the Kalman filter, where we just have one possible hypothesis of the robot and we do what's called the nearest neighbor data association, then we can only commit either on this hypothesis or on this hypothesis here. Okay, and what the fastslam and what the particle filter in this context actually gives you as a plus, as added plus, is that you can have a per particle based data association. So basically you will have a set of different hypotheses on data association granted for free by just using a lot of different samples and a lot of different and a very simple data association scheme. Because when you sample here, some samples will be more on this side, and those will basically associate the observation to these 2. Some sample might be more on this other side, and will associate this observation to these 2. And then you, in a lazy way, you bring all these data association hypotheses forward while the filter operates. And then at the later stage, some samples will actually die out through a resampling process because they will not represent the real world they will not represent in a concrete and consistent way the new observation that we'll collect over time. Okay? And this is actually a more let's say, more realistic example instead of one pose and 3 landmarks. But the idea here is that the pose error is factored out, so you have a lot of potential, a lot of different parts of the state space that can potentially behave or make decisions on their own. And each of these particle is taking its own data association decisions. Now we can see it on a small example. If here, for instance, you can see there is one particle that has associated with this tree. Here there is another sample that might have an association on this tree, and so on. Okay? Again, now how do we do data association on a per particle basis? We can do it in several ways. For instance, imagine now we have this particle here, one observation. These are the estimates of 2 different landmarks. And we can compute, for instance, the probability of the observation coming from the red one, and we can say it's 0.3, or the observation coming from the brown one, which is 0.7. And for computing this probability, you can consider what's called a chi-square distribution and know which is the probability of making a mistake, considering that I have a Gaussian random variables here, and I have a sample out of this Gaussian distribution. So the idea is to compute which is the probability that this sample is within a certain value of the distribution. Okay, so there are some statistical way of computing it using a chi-square distribution. Now what you can do is you can just say I take the most probable one. Okay, so since I don't really need to have any sophisticated data association algorithm on a particle base, because the diversity of the different particles will actually carry diversity into data association itself. Or we can also just say, I have now probabilities, I can just sample. I can say for each particle, I take one sample out of this probability mass here. So 30% of the time I will have this association, 70% I will have this other association, and if you have close by particles, this gives you another small variation into the data association hypothesis, okay? So if your density is very concentrated, what can happen if you do most probable match is that almost all particles will agree on the same decision, so you lose somehow diversity in data association. And if you just do a sampling out of it, then you will keep this diversity into play as well, okay? And the third thing that can happen is that these probabilities are actually too low, so the observation is far away 3 or 4 or 5 sigma bounds of all the landmarks. And then if that's the case, you just consider this as a new landmark and you add it on your state space. Okay, so basically you initialize another Kalman filter and you add it on the particle which had this probability very low. Okay? This is very simple, okay? And as I said also before, it brings almost for free a complex multimodal belief and also a complex multi-hypothesis tracking of all this data association in there, okay? And that's through the combination of having samples and of having a simple rules. You get overall, by considering the all different sample distribution, automatically a multimodal, a multi-hypothesis distribution also over the data association variables. So not only on the landmarks hypothesis or the landmark state estimate, but also on the data association hypothesis. Okay, and that's one of the big advantage of fastslam over EKF, because if we see it from a let's say from a pure state estimate point of view with given correspondences, if we have a very accurate sensor, AKF already gives us a good estimate of the landmarks, as we have seen in the lecture before. But if we start adding a bit of noise and nonlinearities, we have some advantage with the particle filter because we can deal with nonlinear motion better than we can with the AKF. But this also brings a large uncertainty And the most problematic part will be then dealing with data association ambiguity. And that's where fastslam actually, let's say, win the game with respect to AKF-based solution. Here you can see, again, the usual data set that we have seen probably multiple times with the Kalman filter. We have the usual trees, the Victoria Park data set in Sydney, and so on. And again, we can see that everything works fine, everything is perfect, and you can build a map of this park with fastslam. We have roughly less than 2.5 meter root mean square errors, and only used 100 of particles, so it was still a real-time application of the filter. Can I have a video here, just to, again, get you an idea on what's happening down there? So you can still see the, I don't know if you actually see if it's too small, but again, you see how the filter works in practice. We have this blue and red, which are one is the odometry, and the other one is the estimate of the filter, and you can see that we can start estimating the different trees in a correct way. At the beginning, there is some uncertainty, but then it gets slowly down to convergence, and we can see that at some point there is a rotational error down here, and this creates a very bad estimate. But if you have enough particle, we can also recover that, okay? Because there was a lot of uncertainty here. This went on the different side, and we are instead able to have a good result in that. So if we now compare the accuracy of fastslam with AKF on a simulated data, we can see that if we have not enough particles, so in this case we use, for instance, only one particle, which basically means we are trusting odometry. There is not much that we can do after odometry, and is somehow similar to what the Kalman filter will do. No? Because you say, I just have one hypothesis, one particle. It's just that I don't have any measure of uncertainty of this particle. I only have uncertainty on the map. And as you can see, the estimate is pretty bad. No? But as soon as we increase the number of particles, already around 10, we get something comparable with the Kalman filter. And when we bring the number of particles towards 100 or 1,000, we see that we are converging to the same estimate. And in this simulation, we had the linear system, so the Kalman filter was actually the best that we could do in that case. And we also had the known data association. So this is to show the convergence rate of a particle filter. If we instead increase motion uncertainty, so we then get the nonlinear system, we have a lot of uncertainty, and we also add data association uncertainty as well. So where we do not have a known data association variables, we can see that the Kalman filters start to diverge after we add enough noise into the motion. And that's because on one side there are no linearities that is not able to cope with, and on the other side there are a lot of ambiguity of the environment. So once you committed the wrong data association, then it will stick with that and will never be able to converge to the correct solution after that. Okay? While with the particle filter you have different hypotheses, so some of them make a wrong one, some of them make a good one, but at some point there will be a mismatch between what the robot thinks is doing and what is observing in reality, and this mismatch will then bring a weight to a certain particle very low, and during a resampling process then this particle will not belong to the state space any longer. Okay? So, what is, to summarize the fastslam, the main core idea, insight, and take-home message that you should get is that we can use particle filter also for a slam problem, although the dimensionality of the problem actually increases, and you might see that the naive implementation of a particle filter actually needs too many samples to give correct estimates. And we've seen that the SLAM problem actually has an interesting structure, so that we can use this structure to reduce the dimensionality of the state space that we want to sample. So we want to estimate through the particle filter, and we can then we can estimate the statistics of the other part, which is in this case the landmarks, in an analytic way using Kalman filters. The interesting and important aspect is that this is true only if we estimate the full trajectory of the robot. And so we do not estimate just the last pose of the robot, but the full trajectory. And this allows us to exploit this robot equalization, and also allows us to have a very nice and simple way of computing the weights for each of the particles. Okay? So there is no real robot pose uncertainty on each particle, so that's also an important thing to remember and to consider. But the uncertainty over the robot pose is actually given by how this particle cloud is spread over the state space. So you can compute the variance on the trajectory by just computing a sample variance in a way similar to what we did with the UKF, where we had this weighted sum of the empirical scatter between the mean and the samples that we had. And this gives you an idea on how much uncertainty is the robot pose. One thing which is actually instead a bit hard to do is to compute an expected value over the map landmarks. Okay? For a Kalman filter, you will do it. You can just extract the part of the state space that belongs to the landmark. For a particle filter, it's not that trivial because you might have different dimensionalities for each samples. So you might have that one sample has seen 10 landmarks, another sample has seen 11 landmarks, and then it's not clear how to associate which landmark with which other in the other parts of the space. So what people normally do, they do more a maximum a posteriori estimate with respect to the trajectory. So they take the most the sample over the trajectory which is the most likely, or it's according with the part of the state space which is the most dense. And then from this, they then take the estimate that they have from the landmarks out. Okay, so that's another thing to consider. If we see now from a more practical point of view, complexity, we have a total complexity of a particle filter step, which depends on the number of samples that we use, and also the number of landmarks that we have in the map. If we do an update, we have a complexity that only depends on the number of samples. That's clear because we have to apply the proposal for each of the samples that we have. If we incorporate an observation into the Kalman filters, and let's say we know which landmark we need to update, we can implement the landmark list in a vector. We have the index. We just access the index there. So it's independent on the number of landmarks that we have. And we can just, again, have a complexity which only depends on the number of samples. The problem is that when we need to resample the particle set, we need to copy this vector over and over from the different particles. And this has a complexity that depends on the number of samples, because we need to sample and different new samples, plus the number of landmarks because of the copy operation of this vector. So there is a better structure, which is represented by a binary tree in this case. So if we have all the index of the different landmark in a tree, and we just store the statistics at the leaf of this tree, what we have is, when we do a resample, since a lot of particles will share a certain history. So if now the robot starts here, there will be a lot of resampling steps, but the only thing that will change between different particles, it might be the estimate of the landmarks that they are observing right now, but not the estimate of the landmarks that they observed in the past. So we can just take the whole part of the tree, which did not change, and keep it the same, and we will just adjust the pointers of the part of the tree that actually changed. Okay? In this way, we just need to do, in average case, log n operations, log m operations, where m is the number of landmarks that we have, and we get this new complexity, where we have a gain of n, where n is the number of particles for the sampling from the proposal, because again we just need to apply this motion update. When we need to incorporate a new observation in the tree, we now get from n to n log m, and that's because we need to traverse this tree to find the leaf where the landmark statistics are stored. but we gain when we do the resampling, because on average there are only log n block in the tree that we need to update the pointer to the lowest one. Okay, so more details on how this works are on the book, but the idea here is that whenever you touch a landmark, you go up and just update the pointer of the new particle to the subtree that has been touched. Okay, you can see also from a linear memory complexity. The interesting thing is that this not only gives you savings in computation time, but also in memory. And the reason is that a lot of these subtrees will be eventually shared by a lot of particles, by a lot of samples, okay? So if you just store pointers and not the real value, the real structure will still be the same for big chunks of the map, and only few parts which are the latest seen samples, latest seen landmarks will be updated. So we can see that we have a roughly log n for the tree. So this is increasing, but very, very slowly. And we have instead a linear increase in memory when we use the naive implementation with the vectors. Okay? Any questions so far? No? Okay. So we have seen that we use the motion model as proposal distributions. Okay? This is not the only distribution that we can use. So when we implement a particle filter, we're actually free to use any proposal that we want. The thing that we want to care about is to get a distribution which closely resembles the target. And the closer, the better. So one thing that we do not have in this distribution, but we for sure have in the target, is the observation. So the simple, or let's say the first idea that we can come into mind is, can we actually use the current observation in the proposal distribution somehow, so that we can get closer and closer to the target distribution that we want to estimate. Okay? And that's actually the case. There is an update version of fastslam, which is fastslam 2.0, where it's considering the measurement during sampling. So basically we have a Z, the last Z also here. That's different than the full estimate, where we have the sequence of all observation. We're just taking the last one and including in here. We're not going to explain how fastslam 2.0 works in practice. It's a bit involved with respect to the math, but it's written in the book, and you can actually have a look at that if you want. So this is what we add in here. We have a very big distribution, because now if you have a precise sensor, like a laser scanner, for instance, you will have a very precise observation of a very precise measurement of what's around you. The advantages of using a better proposal is that in general you will need less particles. That's because, as also we said on Monday, if the closer the proposal distribution is to the target, the less particle will be sampled in part of the target distribution with low density. So all of the good samples will be in the high density distribution, and when we compute integrals of something which is very close to zero, it doesn't really matter too much, it doesn't change too much the expectations that we are getting under this measurement. It's also more robust, accurate, of course. We are getting more information inside, but it's also more complex. That's why I'm not going to explain it, but it's good that you know that you can use different proposals and what's the advantages or disadvantages of that. You can see here, left and right, the different, let's say, particle sample distributions for the two approaches. So here we can see in red and blue there are different sample trajectories. So the red one is the one which is the best in this case, and you can see that if you use fastslam 1.0, at some point you completely lose diversity of the sample due to a lot of different resampling, because at some point a lot of samples will be in the bad part of the state and we start to converge all of them to just the same sample during the resampling process, and you will lose diversity on the trajectory, especially on the initial part and up here. If you do fastslam 2.0, a lot of samples will be better because they will be sampled from a better distribution. So you keep this kind of diversity in the distribution of the trajectory, as can be seen up here. No? You see you have a lot of more different trajectories where in the part where less landmarks are present. No? So that's another effect of getting a better proposal. If you want to achieve this kind of coverage, we're using fastslam 1.0, you need to use then much more samples, okay? And you will eventually get the same distribution, it's just that will be much more computationally intensive. Okay, so that's a summary for fastslam. We have seen now also that we have two versions of this, which is the 1.0 and 2.0, which basically differ in the way they compute the proposal distribution. We have seen that we can reach a complexity of n log m for fastslam 1.0 by using this binary tree. And this is a complexity, a time complexity, but also a memory complexity. And of course, this is the average case. You can still have a n times m complexity in the worst case scenario where each sample has a completely different history of data association. There is no part of the world which is being shared, but that's a case that rarely happens in practice. If you want to also think on the way this algorithm compares, it scales quite well to the size of the environment. So it scales better than an extended Kalman filter, which basically means allows you to map environments which are bigger, and it's been proven to work in 1 million features or so. Of course, the bigger the environment, the more computation and memory you need. One thing to take into account is also that now the size doesn't matter too much because the complexity depends on the number of samples that you have. So what actually matters is the uncertainty in your estimate. Because the more uncertain you are, the more samples you need to cover a much broader state space. So if you have a lot of an environment which has a lot of features around you, and you have a sensor which is very precise, then you can really push the size of the environment you can map to high number. If instead you always travel in a completely featureless environment where you do not get too many features but it's huge, then you will have a spread of uncertainty which is very big, and then you need a lot of more samples to cover it. So let's say the number of samples somehow relates to the size of the environments, but also on the complexity of the mapping task. The more complex, the more uncertain, the more samples you might need. Another very good advantage is that it's very robust with respect to data association ambiguity, and that's because each sample naturally encodes a different hypothesis in data association. So you have an implicit distribution over data association variables that allows you to perform to have some laziness in the data association. So you do not commit to one decision at one time, but you just bring all the different decisions in data association with you over time until there will come a point in time where it's clear that some of these decisions are actually wrong, and the samples associated with this decision will get a low weight, and they will die during a resampling process. We also have seen some advantages with respect to DKF. One is, of course, this robustness to data association, but another advantage is also the robustness with respect to nonlinearities, because we are not forced to have any parametric distribution, we're not forced to have a linear propagation of the error, but we propagate the uncertainty by just applying the nonlinear function directly to the samples, and this allows us to have a very flexible way of describing and modeling complex distributions in state space. If you want to have a look on the literature, there is this chapter 13 and these sections on probabilistic robotics. One version of the book here has actually some typos, so you should look at the errata corrige to see the corrected version for that. Or you can also look at these two papers, which are which presents fastslam. One is a conference paper, and one is more on a this is one on the fastslam per se. This is more on the data association part. There is also a paper on fastslam 2.0 if you want to get more insights on how this perform and how are the main difference with respect to the 1.0 and the 2.0 version. Okay. Is there any question? No? Okay. So then we can finish the lecture now, a bit earlier than usual, but it's also fine, I guess.